Okay, so we talk about RSA Cryptosystem, which is basically a public key crypto system. Which is a public key crypto system and which was invented by 3 cryptographers at MIT, Rivest, Samir and Adelman. So, based on their name RSA, this crypto system is named as RSA based on their name, and it was in 1977 after the work of Diffie-Hellman key exchange protocol. This was invented by these 3 cryptographers at MIT. Okay, so this is basically an public key crypto system. So, in public key we know that each party has 2 pair of keys. One is encryption key, which is called public key, which has to make it public, and another one is decryption key. So, we have 2 party, Alice and Bob. So, in public key setup, so if Alice wants to send a message to Bob, then Alice needs to get Bob public key. So, what Bob has to do? Bob has to run the setup phase to generate the setup to generate his public key private key pair. So, this is the Bob public key, or it is called encryption key, because this key will be used to encrypt the message by the sender, and this is the public key or the encryption key. And this is the secret key or the decryption key or the private key. So, at the setup phase, Bob has to generate this pair of keys, and then Bob has to make this public key public. Bob can send this public key over the public channel to Alice, or if there is a public key directory, then Bob can store, suppose people public key are stored here, and then Bob can store the public key here. So, Alice can access this directory if Alice wants to send a message to Bob. So, Alice can access this directory and can fetch the public key of Bob, EB can get the public key of Bob, and then Alice will encrypt this message using the public key of Bob and generate the ciphertext C, and this Alice will send it to Bob. So, and what Bob will do, this is the encryption. This is the encryption done by the sender. So, what Bob will do? Bob will receive this message C, ciphertext C, and Bob will apply the decryption algorithm. This is the public key decryption algorithm using its secret key, and this is basically D of DB, C is nothing but E of EB of M, and this should give us M. So, this public key decryption, and this key should be chosen in such a way that they should give us M, and the key should be chosen in such a way that, because this key is public. So, by seeing this public key, one should not able to guess what is the secret key. Otherwise, if Oscar is having this access of this C, and Oscar is also having this E. So, from this E if Oscar can get the secret key or the decryption key, then Oscar can also do this decryption. So, in public key setup, this getting the decryption key or guessing the secret key from the public key should be computationally hard. So, it should be it should not be feasible, computationally infeasible to get the. Okay, so now we will talk about RSA cryptosystem, which is a public key cryptosystem, and we will talk about the key generation for this. This is the key setup phase of this RSA cryptosystem. So, again suppose Alice wants to send a message to Bob. So, this setup has to be done by Bob, so RSA setup, and this has to be done by Bob because Alice wants to send a message to Bob. So, Alice need to get Bob's public key. Okay, so there are few steps. First step is Bob will choose select two prime number, primes P and Q, and usually this has to be a large prime. Why large? We will come to know when we talk about security of this scheme. Okay. Then Bob compute this product P into Q, and then Bob compute this phi n, what is basically P minus 1 into Q minus 1. Okay. And now Bob will choose an integer, E such that GCD of E and phi n should be 1. That means they should be relatively prime. So, this we need because we want to get the inverse of E under mod phi n. So, if they are relatively prime, then the inverse will exist. So, in order to getting the inverse of E, this condition is required, GCD of E comma phi n should be 1. And then, so if this is the case, then inverse exists, then Bob choose the inverse, find the inverse of E, find D such that D is the inverse of E, such that E into D is congruent to 1 mod phi n. So, basically Bob is choosing the finding the inverse of E, which we are denoting by D. So, this is the setup phase. Okay. Now, what is the key? So, key is basically consists of N, P, Q, E, D such that E D is congruent to 1 mod phi n. So, each key k is this tuple. So, this is the key space. Each key k is the tuple N, P, Q, E, D. So, among these who are public, E, N and E is public. This is the public key of Bob. This we denoted by E of B, public key of Bob. And who are the private key? P, Q, D, and this is the secret key or the private key of Bob. So, this is we denoted by E B. So, Bob generate this E B D B. So, this is D B, this is E B, and then Bob sends this E B to Alice, because Alice wants to send a message to Bob. So, Alice got Bob's public key, which is nothing but n comma e. Now the message space is basically Zn. So Alice choose a message m from Zn such that this is relatively prime to n. Why we need this? We will come to know soon when we will talk about the decryption is working. Okay, so Alice choose this. So Alice select a message and Alice wants to encrypt the message. So what is the encryption procedure? Encryption is basically Alice compute so encryption of m using Bob public key. It's basically m to the power e mod n, m to the power e mod n. So e is public, e is known to Alice, n is known to Alice, which is the public key of Bob, which Alice is getting over public channel or from the public key directory. Some way Alice is getting this and Alice is generating this C. So this is the ciphertext Alice is sending to Bob. So this is the ciphertext Alice is sending to Bob. Okay. So now Bob has to get back the message. So how Bob can decrypt it? So this is the encryption procedure, RSA encryption. This is RSA encryption. Now what is the decryption? So for decryption, decryption has to be done by Bob. So Bob is receiving this C. So Bob is receiving this C. This is doing by Bob, and Bob is having its own. This is Bob private key, secret. Bob is having his own secret key. So what Bob will do? Bob will compute. So this is the decryption. Decryption using Bob's secret key of C. So Bob will compute C to the power dB mod n. Bob will compute C to the power dB mod n. Okay. And this is supposed to give us m. We need to verify that whether we are getting m or not. But anyway, this is the decryption process. So Bob is getting C from Alice. Bob is getting C from Alice, which is the ciphertext, and then Bob is having this Bob's secret key dB. So Bob will simply compute C to the power, the ciphertext to the power dB mod n. And so this is the decryption, RSA decryption. And now the question is, why this is equal to m? Why this will give us the original message? So that part we need to verify. So let us talk about that part. Why this is m? So this is the decryption, C to the e to the power b mod m mod n. So C is basically what? C is basically the ciphertext, which is basically m to the power e. Sorry, EB is basically d. So this is C to the power d mod m. Now C is basically m to the power e. So m to the power e to the power d mod m. Now this is basically m to the power ed mod m. Okay. Now ed we know, ed is basically congruent to 1 mod phi n. So from here what we can write? We can write ed is equal to some k phi n plus 1, where k is an integer. Okay. So then we want to use this. So this is basically m to the power k phi n plus 1 mod n. Now this is basically m to the power phi n to the power k into m mod n. So, this we can write m to the power phi n mod n to the power k m mod n. So, but m we are choosing from anyway. So, into m mod n. Okay. So, now this result we know, this is basically we have seen this is the Eulers theorem, and what is phi here? Phi is the Euler phi function. Euler phi function means phi n is the Euler phi function. It is the number of prime which is less than a number of integer which is less than n and which is co-prime to n. So, that we have seen. So, this is basically so this is coming from what is called Eulers theorem. Eulers theorem is telling, because this phi n is basically what? Phi n is basically Euler's phi functions. Phi function which is defined as number of integer less than n, which is defined number of integer less than n which are co-prime to n, which are, that means GCD of n and that number is 1, which are co-prime to n. This is the Euler phi function. And if n is equal to pq, where p is prime, we know if n is prime, then phi n is p minus 1, because so we have seen that. Now, if n is equal to pq, product of 2 prime, this also we have seen phi n is basically p minus 1 into q minus 1. This result we have seen. So, this is basically Euler phi function, this p minus 1 into q minus 1. This one is Euler phi function. So, now Euler's theorem is telling that if we have a let m and n 2 integer such that they are relatively prime, then m to the power phi n is congruent to 1 mod n. M to the power phi n is congruent to 1 mod n. So, this result, this is basically Euler's theorem which we have proved when we discuss the number theory. Then this, so this result we can use here. So, this will be 1 congruent to 1. So, 1 to the power k. So, this is 1. So, this will basically give us m, the message or the plain text sent by Alice. So, this is the correctness of the RSA decryption. So, this is the way we can decrypt the RSA. So, this is RSA decryption where we are using the Euler's theorem. Okay, we can take an example, quick example on this RSA. So, let us take a quick example. Okay, so we have to choose the prime. Okay, so example on RSA. So, same thing, Alice wants to send a message to Bob. So, Bob has to run this setup, RSA setup. So, Bob has to choose the prime. So, suppose Bob is choosing 2 prime number 7 and q is equal to 17. These 2 prime number Bob is choosing, and now Bob is computing n, which is basically p into q. So, which is basically 119. Okay. So, now if Bob is calculating the Euler's phi function phi n, which is basically p minus 1 into q minus 1, which is basically 96. Okay, 6 into 16, so 96. Now Bob has to calculate, Bob has to select a, choose a E such that GCD of E and such that E is relatively prime to 96, because that will guarantee that E has a inverse. So, select E which is relatively, so we select E is equal to 5. So, Bob is choosing E is equal to 5, which is relatively prime to 96. So, that will guarantee that E has a inverse mod 96. Okay, so, now we choose D, we have to calculate D. So, D is the basically inverse of E, we have to choose D such that E into D is congruent to 1 mod phi n mod 96. So, this inverse we can calculate, which we have seen the extended Euclidean algorithm. So, if we apply that, we will be getting D is equal to 77. Okay. This we can cross verify, we can multiply D with this and then we check whether this is equal to 1 mod this or not. So, 77 into 5 is basically how much? 385. Sorry, 385. 385 can be written as 4 into 96 plus 1. Okay. So, this D is can be calculated from which you have seen the extended Euclidean algorithm. So, we calculate D. So, D is this. Now, setup phase is complete. So, Bob generate its public key private key pair, and so Bob generates EB, DB. So, basically EB is basically what? EB is the Bob public key, and this is basically n comma E, which is basically n is here 119 comma E is 5. So, this is sending to Alice. So, this is known to Alice, not only Alice, this is public, everybody knows to, everybody know this comma 5, this is N, this is E. Okay. And then what is the secret key? Secret, all are secret, P, Q, D. So, basically P, Q, D, phi n. So, this is basically so 7, 17 and D is 77. So, this is the secret key of Bob. Okay. So, now Alice has to choose a message which is coming from Zn, n is here 119. So, Alice choose m is equal to 19. Okay. And this should be co-prime to 119 in order to Bob's perform the decryption algorithm. Okay. So, if you do that, then so this is the message Alice wants to send to Bob. So, then what is the encryption? So, encryption is, this is RSA encryption E of m E b, which is basically m to the power E mod n. So, which is basically m is 19. So, 19 to the power E is 5 and mod n is 119. Okay. So, so this will give us 66. If we just calculate this, now this is also another issue, how we can get, how we can do the exponent for the large number. I mean, we will come to that. So, this is 66. So, this 66 is the ciphertext and this is our C, and this is sending to Bob. Okay. So, now how Bob will decipher it, how Bob will decrypt it. So, this is the encryption. Now, the decryption which is done by Bob upon receiving the ciphertext C. So, the decryption is D of DB. So, DB is basically Bob secret key. So, Bob basically used this D. So, C, which is basically C to the power D mod n. So, C is basically 66 to the power D. D is 77 mod n. N is 119. So, this is basically 19. So, this you have to calculate, and if you calculate this, we can easily check this is 19. So, Bob is getting the plain text. Okay. So, this is one example. Now, the question, there are many issues here. So, computational aspect, that means how to, so this is very big number, this is very big number. So, how we can calculate such a to the power b, where a, b are two big number, this exponent, how we can calculate. Okay. And another issue is how to get the primes, because for RSA we need primes. So, we need two primes PQ. So, these are the issues here. So, let us just discuss some of the issues. So, for RSA we need two prime. So, RSA we need two primes PQ, P and Q, and which should be large. Why large? Because so RSA, security on RSA is based on factorization is hard. We have given n, which we know is an integer, which is a product of two prime we know. So, this factorization, if we can do this factorization, then we know the P and Q. If one can do the factorization, then we know the P and Q. Oscar knows P and Q. So, once we know P Q, then we know phi n, because phi n is basically P minus 1 Q minus 1, and so once we know phi n, we can easily compute this, because we know E, we can easily compute the inverse. Okay. So, RSA security is based on this factorization is hard. Factorization is hard. So, if we choose two simple prime, I mean two less prime, say P is equal to 3 and Q is equal to 7. So, then product is basically 21 n. So, by seeing 21, we can guess that P is 3, Q is 7. So, that is the reason we need to choose two large prime. So, PQ should be two large prime, large enough, so that the factorization problem should be hard, it should be difficult. Okay. Now, the question is how we can get the prime number, large prime number, say we need to have say 512 bit prime number, each PQ should be this, not only this, for it could be this bits. So, we need to have a number of this many bits, 01 bits, and it should be a prime number. So, now the question is there any algorithm for which we can give the length of the bit and it should give us the prime of that bit. So, there is no such algorithm which can do that, I mean which can give us the prime number of this much length. So, what we can do? We can do the primarity testing. We can choose an odd integer of this many bits, of the say this many bits, and we can check whether this is a prime or not. So, those are called primarity test. Primarity test. So, in primarity test we give an odd integer n and we test prime or not. So, this is called primarity. There are some algorithm, probabilistic algorithm, Miller-Robin, and there are some recent breakthrough which is deterministic. Miller-Robin is the probabilistic algorithm, deterministic algorithm by Professor Manindra Agarwal from Kanpur IIT and his group. So, they have designed a AKS algorithm. So, they have designed a they have given a deterministic pseudo code which can take a n bit input in which is taking an odd integer and can test whether this is prime or not in a deterministic way. Okay. We will talk about some primarity test in a later stage. Now, another issue in RSA is the computing the this m to the power e or for encryption or c to the power d. So, something to the power b. So, this computation. So, computing this. So, usually these are big numbers. So, m is coming from Zn. So, n is very big number. So, message is very big and e is also big. So, these are very big numbers. So, how we can have a this exponential sum with two big with this big numbers. So, that we have to talk about. And another this properties of RSA is RSA key is basically in PQ ED. So, this is a key space such that ED is congruent to 1 mod phi n. Okay. So, now here we choose E as a public key and D as a private key or the symmetric key. Okay. Now, this role can be changed actually. So, this is the one beauty of RSA. This role can be changed. We can use D as a public key. We just need to choose 2 AB such that A into B is congruent to 1 mod phi n. Then Bob can declare which one Bob wants to be public and which one Bob wants to be kept secret. So, that is up to the Bob. So, this similarity is there in the RSA crypto system. So, this is one of the advantage of RSA crypto system. We can use any of this AB as a public key and the other should be the private key. Okay, thank you.